Okay, well, it's my great pleasure to introduce Professor Andrew Daley. So Andrew is originally from New Zealand, and I think you got your degree from the University of Auckland, and then moved to Peter Zoller's group in Innsbruck. So Andrew was a professor at the University of Pittsburgh, and then moved to University of Strathclyde in Glasgow, Scotland. But I understand now he's in the process of adiabatic transition to Oxford, and he's going to tell us about fast scrambling transitions. Welcome.
Great. Yeah. Okay. Thank you very much. So I guess I didn't have somewhere to pin that. So hopefully the Zoom people can.
We can hear you.
Oops. Can you still hear me?
Yeah, you're good.
Very good. Okay, that's very good. Yeah, so it's a great pleasure to be here. It's been a while since I was last at the JQI, and it's wonderful to see many familiar faces. And I'm looking forward to lots of fun scientific discussions with many people over the next few days. Yeah, so thank you for the kind introduction. So indeed, I am in sort of a classical superposition at the moment, a little bit of sort of moving from Scotland down to England to the University of Oxford. Hence the combination of different pictures. I always like to have something interesting sort of nearby where I'm working on the title slide. So this was Loch Lomond actually up near Glasgow, and this is Keble College. College that I'm at, but also just across the road from physics at Oxford. So what I want to talk about is some things we've been thinking about that involve AMO systems with long-range interactions. I want to talk about the idea of sort of information spreading in these systems with long-range interactions, how it connects to concepts of fast scrambling, and indeed how we can see sort of transitions as we change essentially the range of the interaction from essentially a slower spreading of information that leads to sort of a slower form of scrambling over to fast scrambling, which basically means that the time it takes to entangle the whole system grows just logarithmically with the system size. And then sort of thinking about how this might have certain applications in quantum simulation, or indeed in in AMO systems, sort of building interesting, useful states for metrology or for quantum computing, perhaps. So this is work that was done by a variety of people in my group. This is a slightly older picture, and a few people have moved on to interesting next destinations. And as I say, we are sort of in a bit of a superposition and sort of adiabatically transitioning, as Victor put it, to Oxford at the moment. This is a picture when it was sunny in Glasgow about half a year ago, and a lot of I should say that you do, for group photos, take your opportunities while you can get them. But again, a reminder that this also is near Glasgow, and so indeed there have been a couple of sunny days in the last few years. But it's otherwise a very, very nice place. So the work that I'm going to talk about today was work that was done in the group sort of starting with some things a couple of years ago with Tomohiro Hashizumi, a former PhD student of ours who's now in Hamburg as a postdoc. Sridevi Kuriyatil did the sort of more recent sort of elements of things that I'm going to discuss, and some of it also together with Pablo Poschi and Johannes Komba, who are postdocs within our team. So obviously, a lot of the work we do, we're theorists, but we're very much inspired by what's happening at the moment with highly controllable systems for quantum simulation. And of course, this means sort of a lot of different things that people are looking at, ranging from sort of highly controllable sort of solid state systems. And I know this is sort of reflected by a lot of things that you have here at the JQI, as are many of the other platforms. A lot of the things that I'm going to talk about today are thinking sort of a little bit more specifically about tweezer arrays, or indeed about atoms in optical cavities in order to generate long-range interactions. And you'll see where our long-range interactions in tweezer arrays come from is also not just the fact that you can have sort of rib-big interaction across the system, but also your ability to move atoms within tweezer arrays and create different types of coupling graphs. But the sorts of things that I describe here are going to be relevant to information spreading in any of these sort of highly controllable quantum systems, hopefully also to some interesting geometries that you can make with superconducting qubits or other solid-state systems. Very good. So a couple of questions that are related to information scrambling that I think are really important general questions at the moment involve essentially the sort of question then of how errors and information in general sort of tend to propagate in analog quantum simulators. And one big thing that we sort of set out to look at in some detail that I won't talk about as much today, but I'd be happy to have follow-up discussions with anyone who's interested. It's really, whether we can really sort of characterize how errors spread and how they contribute to sort of overall inaccuracies or imprecision in things that are measured in many-body systems and quantum simulators. And whether we can really then sort of draw up essentially error budgets for many-body systems and ask, are quantum simulators reliable in the presence of noise and decoherence in regimes where state-of-the-art classical calculations are not able to give you reliable results? And sort of I'll say a little bit about the conclusions we draw there and how it's related to information spreading. Also how it relates to the second question, which is the one that I sort of mostly want to focus on today, which is kind of the following motivation. If we have some sort of decoherence in these systems and we just have sort of information spreading sort of from particles to their neighbors and then sort of through the system sort of by neighbors talking to each other, then in that scenario, does decoherence effectively limit the useful size scales for analog quantum simulators? In other words, if you have a certain coherence time and you have a certain rate of transmission of information through the system, does that limit the relevant system size? Is it not useful to build a system of 1,000 spins if you can only entangle 20 of them in the coherence time of your system? And does this create a fundamental problem for how we try to think about building big entangled states in quantum simulators? And if it does, or if it might, at least for certain applications, can we overcome this, for example, by using the fact that in AMO systems, we often have the ability to create long-range interactions. And indeed, that we might be able to create interesting coupling graphs and longer-range couplings also in solid-state systems, engineering them in the right way. Okay. So thinking about just spreading of information, let me sort of go back and remind you, although this is something that there's been a lot of work on also by many people here at the JQI in the last years. If we sort of think about systems with local interactions, information tends to spread by sort of couplings between nearest neighbors. And so you end up essentially with a light cone for propagation of information. And this was sort of first described in this nice paper back in the 1970s by Lieb-Robinson. And they derived this bound essentially, which, and one interpretation of this kind of is the following, that if you start with a whole lot of spins, for example, that are in a product state, and you ask essentially in some type of out of equilibrium dynamics how correlations build up in the system, then there's essentially a limit if you've got a system with local interactions in this form, where essentially you have a light cone within sort of inside of which the correlations can be substantial, and then sort of in the regime outside the light cone, the correlations sort of drop off exponentially. So you have exponentially decaying correlations outside of this this light cone. And you can kind of understand this in the sense of sort of propagation, for example, of quasi-particles within the system. And there's been a lot of discussion as to how to generalize this to systems with longer range interactions. And of course, this is something that is nice when it comes to asking about propagation of errors and how reliable sort of out of equilibrium dynamics are in a quantum simulator. Because if you have this kind of local spreading of correlations, you also sort of have a local spreading of errors that come from things like imperfect calibration of your Hamiltonian parameters. So if you have an analog quantum simulator that's looking at out of equilibrium dynamics in a Hubbard model or in a spin model, and you have calibration errors, or if you're applying sort of local quantum gates, and you have sort of errors in your application of local quantum gates, but you have all of these sort of local couplings, then on a time scale that's sort of shorter than the time it takes for information to propagate through the entire system, the extent to which those errors affect things that are going on in the other parts of the system and therefore combine in an unfortunate way tends also to be restricted. What you find is that that means that things like sort of atoms and optical lattices, when you're looking at out of equilibrium dynamics, and there are calibration errors in your on-site interaction or your tunneling parameters, that the sorts of errors that introduces in the correlations that you get out tend to be significantly bounded. And so you end up with sort of arguments sort of along the following lines that we can really work in regimes where exact sort of first principles classical methods have errors in the sort of correlations that would sort of come out that will grow exponentially after a short period of time where you can efficiently sort of simulate the dynamics. And in this sort of in a more technical paper, we looked at this actually comparing the errors that you got in simulating quench dynamics with matrix product states, where if you don't keep exponentially increasing the resources you have, you get instead an exponential increase in your errors. And you can compare this, for example, to the error budgets that you would draw up for analog quantum simulators, where at short times, those errors tend to be dominated by these calibration errors. You know, sort of things like your on-site interactions and your tunnelings and the different Hamiltonian parameters, typically to of the order of 1% or a little bit less than 1%. But these will give rise to errors, and errors also shot to shot, that, however, don't significantly sort of combine with each other in an unfortunate way, and instead tend to lead in most correlation functions, and indeed often in the fidelity of the state, to an error that is sort of bounded in time. And you can argue this very generally precisely because of these Lieb-Robinson bounds that essentially limit the adverse effects from having sort of local errors in your Hamiltonian dynamics.
Andrew,
Yeah.
this is Bill Phillips.
Hi, Bill.
Hi. So, what's going on with those oscillations, which be in phase for both the fault-tolerant digital and the analog, and well, what's happening?
Very good. So these, as I said, I could give an entire talk on the sort of the analysis of these things, and I'm certainly happy to talk in more detail afterwards. What we're actually plotting here is two-body correlation functions after quench dynamics in a Hubbard model. And the errors here at short times, when we go to simulate the errors in real experiments, they're coming from taking a distribution of possible values for the on-site interactions and for the tunneling matrix elements. And the correlation functions themselves are oscillating, and the period of those oscillations depends on the exact values of the interactions and the tunneling. So what you're doing is you're sampling a distribution of different possible parameters for an oscillating function. And if you ask what the error is as a result of having that distribution, it's going to have the same oscillations that you have in the underlying correlation function sort of superimposed on top of that. If you like, they're kind of, it's almost like having beat frequencies between the exact and the and what you're getting when you have these sort of slightly different parameter values. Does that make sense?
Yeah, sort of.
Very good. Again, happy to talk more about that sort of afterwards. Very good. Of course, the other thing that you get here, and the thing that I'd like to sort of think about more in the motivation here, is the challenges that you have then extending these analog quantum simulations to long times. Of course, if you have a digital quantum simulation and it's error corrected, you can always talk about increasing the resources that you have in order to be able to do a digital quantum simulation with sort of controlled precision, controlled accuracy, and to essentially, really fight in some sense this decoherence. But an analog machine is inherently at some point going to be cut off by the fact that you have some coherence timescale, and that there, you can mitigate that in different forms in the way in which you set up your systems. But at some point, this will be cut off by decoherence. And the question is going to be, well, what can we do to try to make better use of the system despite that? The other thing I should say about this yellow line Here, the errors come primarily from, in that case, trotterization of the fault-tolerant dynamics. And again, the sort of trotterization leads to small errors where the same sort of period of the oscillation, the original correlation functions, is superimposed. The other thing I'll say about this is, of course, the resources required really to do that are well beyond sort of current experiments. Okay, so in some sense, short times, this locality of information spreading in systems with short-range interactions is really good for us because it avoids the adverse effects of errors from different places of the system combining in a way that we would prefer that they didn't. But of course, at some point, if you have decoherence that cuts off the timescale, it's also going to limit the size scales in the system over which you can build up correlations, therefore also over which you can build up entangled states. So the question is, does that mean for an analog quantum simulator that always the relevant size scale of the simulator is limited essentially to the size over which you can build up entangled states within the coherence time of the system? The answer is in some sense yes. And what this means is that for a system with just local interactions, if you double the coherence time, that you would effectively just double the relevant system size. And the question is, can you overcome this by doing something a bit different in systems with long-range interactions? And so this is where we get to the idea of information scrambling, and in particular fast scrambling, and what you might do with those long-range interactions. So the idea of scrambling, how many of you are familiar with the idea of scrambling? Many-body systems. Okay, so about half of you have heard it before. So the idea here is scrambling is something that we have looked at as a way to characterize the spreading of information in out-of-equilibrium many-body quantum systems in the last years. And the idea kind of is this: if I take quench dynamics, sort of starting, for example, with some quantum state on a spin sort of in the middle of a system, and then I kind of look to spread it sort of through the system, you can see that the information about sort of what that quantum state was of the spin here is going to be sort of spread sort of effectively amongst all of the other spins. And of course, you can generalize this. I can take the quantum state of many spins, and then I can spread that information over a large many-body system. And the idea here essentially with scrambling is that we have some sort of dynamics that lead to sort of a spreading of information and a development essentially of entanglement, where the information, if you like, becomes spread amongst all of the relevant degrees of freedom. And that you would expect then development of essentially bipartite entanglement towards what we call the page curve, essentially for all subsystems. And this is not just kind of splitting the system into two and asking how is the left entangled with the right. It's also asking how are these two spins entangled with these spins over here, really spreading information across the whole system. And one way to sort of characterize this is to see to what extent, you know, for all possible subsystems, we've sort of headed across towards this sort of this page curve that was derived back in the 1990s. This is in terms essentially of the von Neumann entropy of entanglement. Who's familiar with that? Okay. Many of you, most of you. So again, the idea here is when you've got an entangled state, you obviously can't write it as a product state of two different parts of the system. What we're doing is we're characterizing how entangled A and B are by tracing over one half of the system. And if these are entangled, if this is not a product state, then you are going to have then a mixed state. Once you've traced over sort of part B of the system, you'll have a mixed state for part A of the system. This is characterizing how mixed it is by stating the von Neumann entropy of entanglement. And the bigger this is, the more entangled these pieces are. So long as we had a pure state for the whole system, and for the moment, everything I'm going to talk about is in terms of pure states for the whole system and dynamics that are evolving. And so what we expect is to get something that, that is going to go essentially as this type of volume law, where the von Neumann entropy of entanglement increases proportional to the size of the subsystem for all sort of possible subsystems. Now, This has a lot of different connections across different things that people have been interested in out of equilibrium dynamics in the last years. And one reason why it's important, going back to the sort of comparison of what you can do in an analog quantum simulator or a digital fault-tolerant quantum simulator compared with classical calculations, is identifying that when we do calculations with things like tensor networks with matrix product states, that the more entanglement we have across any possible bipartite splitting of the system, the harder it becomes to do those calculations. If we have limited entropy of entanglement across certain combinations of bipartite splittings, then there are generally ways to build tensor network unsets in order to more efficiently classically simulate the system. But if you have a phenomenon entropy of entanglement that grows linearly in time, then the size of the matrices that you need in a matrix product state, for example, or in a tensor network in general, in order to represent those states grows exponentially. So the computational resources you need grow exponentially in time.
So if you were to do something like this just by hitting a system with random matrices and producing completely chaotic dynamics, would it qualify? I don't know. You thought about it or looked into it, but would it qualify as fast scrambling or slow scrambling? Or
so people, for example, take random circuit models as a really great example of fast scrambling. You can ask, of course, if it's a useful example of fast scrambling, and I would say that for theoretical characterization of fast scrambling, it's useful. For building interesting entangled states, it's probably not so useful. But yes, I'll come in a moment to the question of how you demonstrate fast scrambling, and indeed, you can look at all of the sort of random quantum circuits that people have done in order to demonstrate quantum advantage, and say these are examples of scrambling dynamics.
Andrew, this may not be the right time to ask this question, but I'm going to ask it anyway. It seems as if there's a kind of a tension between being able to entangle a big system, which is obviously a good thing when you're trying to do at least certain kinds of quantum simulations, and having the system decohere in a way that's going to mess up your calculation. Is that, have I mischaracterized this, or is
so what I would say at the moment, in the way in which I'm characterizing this, what we would like to do is find a way to build the entangled state as fast as possible in order to circumvent the fact that decoherence is going on. And so especially if the decoherence has some sort of fixed origin, ultimately, that is different to the dynamics, or indeed, as we'll come across in a moment, if it sort of is proportional to the number of operations or the number of couplings you need to have, then the whole idea is then, can we build this entangled state faster in order to circumvent the decoherence? Does that make sense?
Yes, it does. But at the same time, you told us earlier that if you had long-range interactions, then you were going to decohere the whole system faster. And so, I mean, I guess it's just a matter of what beats what.
So it's let's come back to this in a moment.
Okay.
And I can explain in a little bit more detail. But the point is sort of the following: that that what I said before was that the locality is kind of nice, because if you haven't spread information over the entire system at a particular point, then the errors will not have spread over the entire system, and therefore will not sort of be adversely affecting your dynamics.
Right.
Once you spread the errors over the entire, or the level to which they can adversely affect your dynamics is restricted. Once you've spread information over the entire system, once you've entangled the entire system, you've also provided the opportunity for errors to spread over the entire system. And so at that point, this argument sort of breaks down, irrespective of whether you did it with long-range interactions or whether you did it with short-range interactions.
Okay.
Okay. And now what I'm going to argue in a moment is that it's better to do it with long-range interactions, because if you do it with long-range interactions and you can build this up in the sense of fast scrambling, which means that the amount of time and therefore also the number of effective operations that you perform sort of grows sort of logarithmically with the size of the system, then what's happening is that if you've got just a background decoherence rate that you can't get rid of, then you simply beat that decoherence rate with this sort of scaling of the timescale to build up the entangled state. And at the same time, if your errors were coming from calibration errors in the individual operations themselves, then if you were doing this just by locally spreading information through the system, then the total number of steps that are required to spread that information grows, per qubit or per spin with the size of the system. Whereas with the long-range interactions, the total number of operations I need to perform just grows logarithmically with the size of the system. So I perform fewer operations that introduce, therefore, fewer calibration errors.
Okay, great.
So in fact, you win on both counts.
Thanks.
Okay. Right. So the question, of course, is, though, how do you really realize sort of fast scramblers, in particular ones that might be deterministic or do something useful in building up useful entanglement then in real physical systems? And this is sort of, again, one of these things. A lot of people have discussed scrambling in ways that are very interesting in terms of the physics for random operations or with disorder. But especially if you want to talk about it, having an encoder for useful entanglement, what you would like to have is ways to spread information around the system on a time scale that only grows logarithmically with the system size, but that actually is deterministic. And so what we set out when we originally started to think about these things was we set out to try to create a way that would allow us to generate an entangled state over the whole size of the system in this sort of time scale, which grew only logarithmically with the size of the system, but which was based on deterministic operations. So we weren't just doing something random, but we were building things that could be adapted to generating interesting specific entangled states. Okay, and of course, just this kind of side note that I won't talk so much about here, that originally this idea of fast scrambling came up in considering quantum information in black holes in various papers going back almost 20 years. And that's where the sort of conjecture of sort of fast scrambling being sort of the fastest way to generate entangled states, essentially things that grow again, with the time scale to do this grows as the logarithm of the system size. That's where this sort of originated. But what we're going to be doing is trying to reproduce this now, but in AMO systems. So there are various ideas for studying fast scrambling in recent years. Some of them sort of connected to random spin models, such as the SYK model. Some of them connected to random circuits. And there was a lot of really interesting work. And if I tried to put all the references down for everything that had been done, it would take probably about 3 slides. This has been a big topic in the course of the past few years. About sort of 5 years ago, there were a series of groups, including some people here at the JQI, who started looking into the question of whether we can find a way to sort of, have fast scrambling, but without disorder, by combining sort of interactions on different length scales. And so there were proposals, for example, to combine sort of nearest neighbor couplings between spins with a cavity with all-to-all interactions. This was work in Alexei Gorshkov's group in collaboration with various other teams in different places, and there were various other sort of attempts at this. What we did together initially with Greg Benson, Emily Davis, Monica Steyer-Smith, with Tomohiro and Anton, and also with Steve Gubser, who unfortunately passed away just towards the end of this work, was to think about sort of long-range spin models that could be generated with AMO systems, initially with sort of spins in optical cavities, and then later, together with Tom, Greg, Sebastian, and Sridevi, thinking about how you might sort of build up some of these things with moving atoms in tweezers. And in each case, what's happening is we're generating long-range interactions in a systematic way, either by driving atoms in a cavity in a gradient field, or by moving atoms in an optical tweezer array. And the idea is to have long-range couplings, but if we couple just all atoms in an all-to-all way, then all we do is get a symmetric spin model that rotates things in a symmetric subspace sort of about whatever the initial state was. It is therefore, if you don't break the sort of symmetry somehow of all-to-all interactions, it becomes very difficult to build up these sort of big entangled states. So we needed to find a way to break that symmetry, and the way that we do it in our models is we only couple some of the spins. So we create effectively a sparse coupling model where we can have couplings over long ranges, but where only some spins are involved. So in the cavity case, what we chose to do was to think about coupling spins that were separated by powers of 2. So what you do here is you essentially drive a cavity at multiple frequencies whilst having your atoms in a magnetic field gradient, which means that you have a range of transition frequencies sort of across the system. And so you can then effectively dial in different couplings by having essentially some central driving frequency that is coupling sort of spins between two states, and then have essentially sideband frequencies where the differences from the sideband to the carrier correspond to the sort of difference in transition frequencies of the atoms at different places in this magnetic field gradient. If you do that, you can effectively dial in essentially different couplings as a function of distance. This idea originated actually with this paper down here, where people were thinking about sort of photonic waveguides and a variety of other possible systems. What we did was sort of adapt this to thinking about how you would sort of build models in an optical cavity, and in particular, these types of sparse coupling models. So the idea here is twofold. Firstly, well, you can dial this in so that you only couple if the spins are separated sort of on a discrete line by a power of 2, that is if they're neighbors, or if they're 2 spins away from each other, or 4 spins away from each other, or 8 spins away from each other. And we can also think about having coupling graphs here where you perhaps weight the strength of the coupling, that this could decay with distance, but it could also, because you're just dialing this in, it could increase with distance. So we started to look at these spin models where you could have interactions that decayed with distance, or that increased with distance. And we started to look at the spreading of information in these sorts of models. Yeah.
So is the goal here to saturate this fast scrambling conjecture, sort of, or what is you're trying to do?
So the idea is to saturate the fast scrambling conjecture, but also to understand what the requirements are, to understand whether what level of long-range couplings we need for this, and also to do it in a deterministic model where we're not putting in random couplings, and so therefore where we could also use this as a way to encode interesting entangled states, maybe by changing the dynamics a little bit away from the sort of specific conditions for scrambling, but still use it sort of as a coupling graph that we can use to build useful entangled states.
And this particular interaction sort of structure, is it dictated by experimental sort of constraints, or is there some theory intuition why I should do this and not whatever else?
So this is actually really interesting. So experimental constraints sort of, in this particular case, we were able to generate sort of whichever models we wanted to look at. And you'll see that we actually chose specifically a hypercube geometry, which was related to the experiments when we started to think about tweezers. Here, the power of 2 models were actually inspired by Steve Gubbs's work thinking about two-adic field theories, which is essentially field theories over discrete spaces. And the idea that actually, in fact, this sort of regime of decaying interactions here, this regime of interactions increasing with distance, actually almost gave you something that looked like a transition between two different types of spatial geometries for how the spins were coupled. And so this was the intuition behind it. And now I'm going to explain it on this slide by going back almost the opposite way. Okay, so if I have interactions that decay with distance, if they decay rapidly, then I've effectively got something that looks local. And so here's sort of something that decays with this sort of with the power of 2, essentially. So I minus j to the minus 2. And you can see what I end up with is effectively this light cone like I would have in a system with just local interactions. If I make this, if I send this s to minus infinity, it really is just nearest neighbor interactions. On the other hand, if I go the other way and I increase interactions with distance, you could say, oh, well, this looks great because I'm now spreading information really quickly across the whole system. But if I'm doing that, I'm cheating because now the spins that are most strongly connected with each other are no longer sitting next to each other the way I'm drawing the line. So what I should do is actually rearrange my spins. So in this case, where the interactions increase with distance, I should really, to be fair, rearrange my spins so that the ones that are most strongly coupled are sitting next to each other. And if instead I do that, then I recover something that, again, in this type of regime, just kind of grows with a light cone, essentially with graph distance. Okay, so that in fact over here, oh well, actually here also it's a light cone with graph distance. We'll come back, but so here essentially information is being spread very, very rapidly between certain combinations of spins, but they are rather disconnected from the rest of the chain, and you can see that here with all of this kind of black space with no correlations in the middle. Okay, so this increasing interactions with distance doesn't help. It just gives you local spreading of information, but in a different geometry. But this s is equal to 0 case is very interesting because it almost becomes like the transition between these two geometries. And now you've got a graph where to get from anywhere to anywhere else on this graph requires a number of hops that grows only logarithmically with the system size, and where you don't have sort of obvious symmetries in sort of how to take a bipartite splitting of the system, because you can't do sort of something in this type of geometry and you can't do something in this type of geometry on the two sides. It's almost sort of a transition point, which makes it kind of more interesting when you're trying to look for something that scrambles information. And again, if you look at this, it all makes sense in terms of graph distance. In this particular case, with a lot of locality, if you really map it back onto the onto down here, these sorts of systems where you put the spins that are actually most strongly coupled next to each other. Okay, so the point is when you start to do calculations, what you find is that if you look at all possible bipartite splittings of these systems, that the most complicated things over all splittings, okay, so there are obviously, if you try to rearrange the spins and make them look like they should for, make them look like they should when you have interactions that increase in distance, but do local interactions in space, you can get a lot of entanglement over some splittings. But the key is you get entanglement that is very strong over all splittings if you sit at s is equal to 0. And so this is sort of the area where we expect to see that sort of scrambling. We can do the same thing, but not on the power of 2 graph if we take atoms and optical tweezers. And the idea that we came up with here was to build these things, obviously not by sort of dialing in interactions in cavities, but instead by using moving of atoms and optical tweezers. I said to Michael this morning, it was quite funny. We wrote this paper in 2021, and when we first started to talk about it, it was just a little bit before the nice results from the experiments at Harvard, where they showed that they could maintain coherence whilst moving atoms in tweezers. And the number of times we then got asked by people in the audience, aren't you being totally silly as theorists? Do you think anyone's ever going to be able to move atoms in tweezers whilst maintaining coherence? It was sort of quite funny. We had good justifications, we thought, but of course, there's nothing like having someone actually having done the experiment, because now people don't ask that question anymore. They have other questions, but so this is really nice.
So Andrew, one of those other questions might be, well, it takes a certain amount of time to move atoms with tweezers.
Yeah.
So just because you've got the capability of connecting things that are distant doesn't really mean you've beat some kind of Lieb-Robinson time limit, because it depends on how fast. And of course, there's adiabaticity constraints and whatever. So there must be some rules.
So the rules are effectively this: so long as you're doing the whole experiment in a timescale that is short compared with the overall storage coherence time of these atoms. So if your entanglement lives for tens of seconds, if you just sort of leave the atom sort of sitting in the tweezers, and these sort of shuffling operations take only milliseconds, then you're going to win by doing it this way rather than spreading it from place to place through the system, because the time scale that it takes to entangle the whole system grows as in terms of the number of operations you need to perform to entangle everything across the whole system, grows as the logarithm of the system size. So if you've got 64 qubits and you leave them sitting where you are, you need to have essentially gate pulses, or time of the qubits interacting in the excited state, proportional to that. So a time scale of the order of 64 times the interaction times. Whereas here, to do the same thing, you would need something of the order of log of that number. So in that case, 6. And if it's approximately sort of twice that, which is what we find numerically, then essentially you're going to have of the order of sort of 12 excitation pulses, as opposed to the order of 64 excitation pulses. And of course, if you grow the size of the system, that only becomes more and more favorable to this. So the time spent in the excited state, which is the worst sort of fundamental limit for these Rydberg systems, it goes here only as the logarithm of the system size rather than proportional to the system size. And the same here is true essentially for building any sorts of states with it. The only problem that you have is that if you're using timescales now of the order of milliseconds rather than of the order of microseconds, you might ask, how does the total time compare with the several seconds of coherence time you have in the system, rather than sort of being, so I'm comparing milliseconds to seconds rather than comparing microseconds to seconds. But so long as that millisecond value is still small, you win, because here most of your fundamental error comes from performing gate operations, exciting atoms to the excited state. And you're substantially cutting down on that by doing it this way.
Right. And if I've understood correctly, one of the key advantages then is in that when you're moving the atoms, which might take a long time if you don't want to excite them vibrationally, you're doing it while the atoms are in the ground state, so you don't have to worry about that decoherence.
Exactly. So for these Rydberg systems, I'm worried about exciting them really to a Rydberg level from which they can decay, which is both the fundamental source and the major technical source of error in these experiments.
Right. So this wouldn't apply to a lattice of atoms where the interactions were not mediated by having the atoms in a Rydberg state, but it works very nicely in this case.
Exactly right.
Okay,
yeah.
Super. Thanks.
Brilliant. So Bill basically asked most of what I was going to say on the next couple of slides, but it's always nicer to answer the questions in that way, I think, anyway. So here what we're doing is we can realize fast scrambling, it turns out, just by having essentially these combinations of the reshuffling operations and then excitation pulses that do gates between neighboring atoms. And we find that actually with essentially two rolls through the circuit, that in fact, what we can do is generate a state scramble to the page limit. And the moving atoms, exactly as Bill just asked, moving atoms cost time, but saves gate operations and therefore Rydberg excitation time, which determines currently both the technical and the fundamental coherence limits in these experiments. And that's why we win. We scramble to the page limit, and we can talk sort of technically about how we looked at this. We looked at this mainly for Clifford circuits in this particular case, and then you can scale to big system sizes and see that this really acts as a fast scrambler, despite the fact that we're using here deterministic operations, essentially on all the lengths of the effective hypercube graph that we get by moving atoms. So two questions sort of remain for this type of thing. The first is, can we see a transition to fast scrambling? I've talked to you about how I don't expect to see fast scrambling if we've got short-range interactions, and I don't expect to see fast scrambling if we've got long-range interactions. Can we actually characterize a transition that tells us as we go towards having this kind of limit where everything is equally coupled on our graphs, that we get a transition? And the other question is, can we actually build a useful state with this and not just actually sort of scramble to something that is just a state that has a lot of entanglement, but that I don't necessarily know how to use to do something other than study fast scrambling? So can we see a transition? So again, we can sort of start to look at this. If we want to do it for big systems, we do have to kind of pay the price of going to probabilistic applications of gates in order to get this weighting of the couplings over different distances. So we do that so that we can still work with Clifford circuits, but we're now actually in the process of looking at the same thing, but with continuous spin models, just for smaller systems where the scaling is a bit harder to see. And again, what we find is that we get rapid development of entanglement across all sorts of subsystems when we have these equal sort of interactions at the different distances, and we get different levels of entanglement for different subsystems if we have the structure by having local interactions in real space or things that are local in this mapped space. So can we characterize this transition? And we can, using a fun quantity called the tripartite mutual information. Who's heard of the tripartite mutual information? Yeah, several of you have worked with it before, I know from your papers. So for those of you who are not so familiar with it, the question essentially is this: embedded in a bigger quantum system, what the tripartite mutual information is trying to tell us is that essentially if there's some sort of entanglement, then there's some sort of information, it can also be classical correlations, but some sort of information that subregion B is going to have about subregion A, through the way in which they're correlated. And there's going to be some level of information that subregion C has about subregion A because they are correlated. And you can also ask how much information do subregion B and subregion C, which in general are themselves entangled, have about subregion A. And it's essentially asking the question, is information spread across the system in such a way that regions B and C combined know more about A than C and B do on their own? And where you do have this, it means that there's some complicated non-trivial entanglement. If you just shared Bell pairs between different regions, this would be 0. Okay, this value would always be 0 if you only have Bell pairs. And so you need to have some other level of entanglement between regions B and C to make this different from 0. And so it's really characterizing the level of scrambling. And when this goes negative, it really tells you that information is sort of spread through the system. And what we do is we've looked at this in a random circuit model. We've looked at it on a power of 2 graph. We've looked at it for the hypercube graph. And what we find in each case, as we change the sort of this value of S and bring it from local interactions to something that goes closer and closer to 0, is we find that for the couplings being more local, this tripartite mutual information scales to 0 as we increase the system size. But past a transition point, this tripartite mutual information increases with increasing system size. And what we're doing here is taking of the order of a single gate operation performed per qubit. So it's really just telling you about the structure of information spreading on these graphs. And when we do that, what we find again is really this transition. So this sort of point where all these curves cross really marks a transition where to the left here, we've got local interactions and, if you like, slow scrambling. And we really have this transition into this regime of fast scrambling. What that also kind of tells you is the level of non-locality that you need in the interactions, which is going to depend on the details of the model in order to generate fast scrambling. And but what we find is that across all these different 3 graphs, we find that type of behavior. And you need to go to bigger system sizes in some cases to see it than to get into a universal regime than you do in other cases. But you see this again also on the hypercube coupling graph, which would require essentially different rates of applications of gates at different layers of our shuffling process. The final question is, can we do something useful with this? And the answer, depending on what you consider as useful, I think is yes. And what we've been specifically thinking about is the production of entangled states for metrology. So we know if we put atoms in a cavity, we've got all-to-all interactions. We can build spin models that after a time which is sort of fixed, independent of the number of atoms, because these are just all-to-all couplings, we can generate GHZ states which have a high quantum Fisher information and are useful for metrology. If we just put the right sort of spin model in, if we put an XY model in and just have nearest neighbor couplings, that will build Fisher information, but you won't get to a GHZ state just with sort of nearest neighbor couplings. It turns out that the spectral gap essentially that corresponds to staying in a subspace where you will produce a GHZ state is significant independent of system size. Also, if you have these sorts of power of 2 type couplings, and that in fact you do protect the dynamics in such a way that you still go up to something that is almost exactly here, a GHZ state with the same Fisher information as what you have in the all-to-all case. And you can build this here in this sort of protected way in a timescale that grows just logarithmically with the system size. This is a nice way of building a GHZ state if you've got all-to-all interactions because you've got atoms in a cavity. What this tells you is you can try to do exactly the same thing, but now with atoms in tweezer arrays, just shuffling them and building this type of XY model.
Do you know what's the optimal measurement for those states? Like, are they really like GHZ states, or this effort to be more complicated?
So these are GHZ states, and these here in the plateau are basically sort of the compass states wrapped around the equator of the block sphere. This is the quantum Fisher information. So in that sense, the optimal measurement here is to try to do a spin rotation that shifts them away from the axis where they are. For example, if you have the compass states, you want to try to rotate the compass state, and then essentially the optimal measurement is always if you can take a projection back on the original state. And so one way to build a protocol that would do that is that you would build up these states, entangling them, that would give you the resource state. You would then apply the sort of rotation to measure, okay? And then you would precisely undo the encoding steps that produce the original state. And in principle, that builds up essentially a projection back onto the original states. If you'd started, for example, with all spins down before performing a series of operations that gave you those states, you would then ask, what is the projection back onto all spins down? And that's something you can measure just in the Z basis. So in the worst case, you have an encoding and a decoding stage. There are probably more clever ways to do things if you wanted to simplify the experiment. Great question.
I guess since we're working projects, maybe the answer is not clear. So after all these operations, if you have any error, they would propagate also in the system. And similar to just the normal GHZ, it would be probably very prone to the
So yes, okay. I think that as any normal GHZ state would be, it would be relatively prone to the errors. What I would say we've just started some initial sort of testing of to what extent this is sensitive to sort of small errors in the Hamiltonian parameters or in the implementation of the gates that are building the states, and that doesn't seem to be so bad if it's really just those local things. Of course, if you had decoherence or things that would measure individual spins, then it would be very prone to that, especially when you're in the GHZ limit. Yeah.
But why do you have an intuition?
So in the same way as you have over here, there's effectively a spectral gap which I think protects this dynamics that take you into the GHZ state. And in the all-to-all case, the spectral gap increases with the number n. The gap actually goes to 0 as you increase n in the nearest neighbor case. But in this case, it actually stays constant with increasing n. Okay, so these dynamics are in a sense protected to for small changes in the Hamiltonian parameters. And we need to do some more testing of this. In fact, what we tried to do is ask, is there a halfway house between the scrambled states and the GHZ states that would combine GHZ sensitivity to the measurements you wanted to perform, and the scrambled states kind of robustness or protection against sort of decoherence. But it seems that there's no free lunch here, that you either have a sensitive state that is good for metrology but is also really bad at decohering, or you have the other side of things, something that's no good for metrology but is kind of robust in its entanglement. What I would say again here is that there's an important comparison in how long it would take sort of to do things with nearest neighbor interactions versus if you've got these sort of order of log n couplings to produce your states. And just as an aside, though that was a calculation in a spin model, but of course you can actually implement it in these sort of shuffling operations by effectively trotterizing it. Okay, so you just break it up into steps, and then you can perform it essentially in these in these different sort of shuffling steps. And if you do that, you can ask, well, how large an evolution can I have in each of these sort of preparation steps before I start breaking essentially the spin model dynamics. And so this is essentially a test of that. And we find that that you're going to need to have the order of about sort of 5 or 10 of these different steps and trotterizing it in order to still maintain the spin model dynamics. Okay, with that, we are almost at the end of time. I just wanted to say, because I'm here for a few more days, we've also been doing a number of things, thinking about quantum control, thinking about implementation of quantum gates and RIB-big systems, and doing corresponding atomic physics. I'm still very interested in open quantum systems, including ways to characterize and simulate non-Markovian dynamics and ask what information you get out of a non-Markovian system that sort of then has a Markovian coupling at some point to a reservoir with detectors. We have various things we've been playing with on that. And we've also been thinking about various things in quantum transport dynamics connected also to some of these sort of open quantum systems techniques. And with that, I just wanted to summarize that it's been fun trying to think about these long-range AMO systems. They're really fun experiments to be thinking about as a theorist. And this idea of fast scrambling is sort of a fun one to play with, has a lot of connections that we're sort of starting to try to make more sort of couplings to here. But that what is clear is that there seem to be, ways in which if you can build these sort of long-range coupling graphs, it really can give you an advantage in building big entangled states. And this is something sort of fundamental that in tweezer arrays, that being able to move atoms buys you, that you don't get if you just have the nearest neighbor couplings. And I'm also curious as to whether there are ways to engineer sort of some of these architectures with longer range couplings also in the solid state. So questions for the solid state experimentalists about whether some of that could be interesting in that context as well. Thank you very much.
Kind of follow up to your last comment on building this in solid system, and I guess this is also my confusion. Like, Because people talk about waveguide QED, like using superconducting qubits, that in those kind of scenarios, maybe you can imagine building like a bit longer range detection, but they always usually come with like other like dissipative mechanisms that are sort of powerful as well. So I'm curious, like if you have any comment on like, should I worry about those kind of sources at some point, because those refer like they are large, but they're maybe not that large. Like will that eventually become like a source of error, and also like maybe one can like imagine doing it like it's working on qubits. If there are ways to suppress those like non-local.
So I think that's a really important set of questions. So
could
part
you
of our reason
summarize those questions? It was a little hard to hear
sorry.
online.
They were very clearly and articulately stated with a lot of connections. The central bit that I'm going to answer is kind of the question of, should we be worried about, if we're generating long-range interactions with, for example, a waveguide and circuit QED or something like that, we're worried about the decoherence that comes as a result of that. Should we be worried about that in the context that we're discussing here? And should we be worried about also, for example, what the dissipation is going to do on the Rydberg side, sort of in addition to the cavities? So Monica and her team have been doing beautiful experiments in these cavity systems. At the moment, most of it has to do with collective spins, because if you could compare the single spin coupling, essentially, and they're in the strong coupling regime, but compared with the effects of the decoherence on this many-body dynamics, if you just try to do it with a single spin half, at the moment, the dissipation is a bit too strong. I think cavity QED might actually be in a slightly different parameter regime if you did that. The way to compensate that and still look at some of these dynamics is to have clusters of atoms that give you a higher spin than just spin half and look at these same sorts of dynamics. And so that's sort of closer to what Monica's been doing recently. And there's some beautiful experiments that initially realized this and have gone on from that.